Hello, today's lesson is on algebraic vectors. So, what's your goal today? I want you to be able to do three things. First thing is I want you to be able to write a vector in ordered pair form. I want you to be able to write the vector in unit vector notation. And then I want you to be able to complete some operations using some of our basic algebra operations from grade 9 and 10. So those are the three things I want you to be able to do. So the first thing we need to go through is we need to talk about the two algebraic forms of vectors. So there are two forms. One's called ordered pair notation, and the other one is called unit vector notation. So ordered pair notation, if you were to draw a vector, and let's draw them in the same quadrant. So if I draw this vector, and the end coordinate here, let's pick a couple easy numbers. So that looks like a 5 and a 4. And I do the same thing on the other grid over here, 5 and a 4. What I want to do then is I want to write them each in the associated format. Now if we use that as our end coordinates, this translates to approximately 39 degrees, and for our situation that's good enough. Okay, so ordered pair notation. With ordered pair notation, the vector, our vector, is written as if the tail is at the origin. It's at the origin. And head at the end coordinate. Okay, so if I call this vector u, then my vector u is equal to the vector 5, 4. Okay, one thing I want you to note here, for this course, for MCV for you, we always indicate a vector with square brackets. Okay, so if you see square brackets, we're dealing with a vector. And if you're dealing with round brackets, it's a coordinate. Now, that is for this course only. Okay, in the real world, you can actually use both notations. Both are correct. You can use square brackets and round brackets to indicate vectors. I just find this initial process when you're learning how to use vectors and write them makes life a lot easier if you're able to easily distinguish between them. So I am going to use square brackets all the time with vectors. So if you see round brackets, you know you're dealing with coordinates. Okay, but when you move on to university next year and you're dealing with vectors, it can be either or. So don't be putting up your hand telling the professor they're wrong. Okay, unit vector notation. Unit vector, what we do is on the x-axis, we state that I hat, so unit vector I, its magnitude, the magnitude of the I, magnitude of the unit vector, magnitude of our unit vector is equal to 1, and direction is down positive x-axis. So I'm going to tell you that this direction here, my unit vector I, points that direction. On the y-axis, we state that j hat, which is the unit vector j, the magnitude of j is 1, and direction is up positive y-axis. So this one's more like a road map. How do I get from origin to the head? Well, I have to go down the x-axis 5 units, so 5 i's. Because I tells me it's down the x-axis. I don't have to tell a person that. As soon as you see I, you know you're moving down the x-axis, and I'm moving 5 units. Then I have to travel up 4 units up. J again gives you direction. So in the end, this vector is, vector u is equal to 5i plus 4j. Exact same as the coordinate form. The difference is this one involves i's and j's, and this one just deals with the x and y component. So 2 forms, and you can use either or. I'm never going to tell you which one to use. Both are correct. And the I is your x-axis, j is your y-axis. So in 3 space, what happens if we have a coordinate that is, this is my origin. I'm always backwards to the textbook. Try my best. I think this is the x. Then they have, this is the y, and this is the z. If it's not the same as the textbook, it doesn't matter. It all shakes out in the end. But let's say we go back some negative distance here on the x-axis, and then I move up on the y-axis in the positive direction, and then let's move forward in the z direction. So I'm drawing a 3D vector. So that means that my vector starts at the origin, and the head ends at my endpoint. If I continue or finish the shape here, what we find is that this vector that I've just drawn is in a shoebox. Okay? It's inside a shoebox here, and we're going from the bottom corner of the shoebox to the top corner of the shoebox. All right, so a 3D vector, and what happens then is their 3D vector has 3 measurements involved. It's got the angle with the x-axis, so this angle here. It has the angle with the y-axis, which is here, and the angle with the z-axis. So if we give them each a value, so we'll call that theta, alpha, and beta, and it does not matter the order, at least not in this course. I'm not too concerned with that. So how do you find the magnitude of our new vector here in 3 space? Well, to find it, if you recall back to grade 9, this is a thinking question in grade 9, you had to find the distance across the bottom of the box because you knew this value and you knew this value. So I'm telling you that we're going to use the z value. So this is our z value, and going back on that axis, that's our negative x value. So to get the hypotenuse, we'll call it an h. So the value or magnitude of h is equal to, and it's a vector, magnitude of h is the square root of our z value squared plus our negative x value squared. So it's just using Pythagorean theorem, which translates to z squared plus x squared. So that's the magnitude of that hypotenuse. So now, if I can get a different colored, these are happy faces, I now know the length of that vector. If I then know the height of it, I can then find the hypotenuse of this new triangle, which I'm going to call vector u. So the magnitude of vector u is equal to, again, Pythagorean theorem, the square root of this component here, which is our y, so y squared, plus the length of that hypotenuse, the length of the happy faces, which is our h value, and I just said that's the z squared plus x squared, and that would be squared. So when you simplify that, the square root and the square here are an inverse operation. They undo each other. So we end up with the square root of y squared plus z squared plus x squared, or we usually write them in order, x squared plus y squared plus z squared. So you just have to take the 3 components from that coordinate, which would be given. So the end coordinate would be your x, your y, and your z value, and you use them in that formula to find the magnitude of a 3D vector. So I want to make sure that gets or makes its way onto your cheat sheet. The second component here, the direction vectors for a vector in 3 space. Direction vectors are tied back to those angles. And the nice thing is it's direction cosines. So everything's a cosine here. So with that gobbledygook here, if you can follow along with that diagram, the theta, which was the angle that the vector makes with the x-axis, we'd end up doing theta would equal cos inverse of the opposite length. So that's going to be your, when you're looking at it, we know in this case, we know our value along the x-axis because it's adjacent over hypotenuse. So it will be our x value over the magnitude of the vector. I said that phi was the angle with the y-axis. That's going to be cos inverse of y over the magnitude of u. And remember, you don't need a calculator, or we're not using calculators, and that's where your answer would be left with those values. So your z over magnitude of u. All right, so this is the angle with the x-axis, y-axis. The curriculum doesn't really state to take it much further than that. You just need to be aware of what they are and how to calculate them. So there you go. So your x-axis, y-axis, and z-axis. And this last part, I'm going to worry about it a little bit later on. So we're not going to worry about that right now. All right, so there is magnitude of a 3D vector and your direction cosines. And the question in the textbook and in the test will be just calculate the direction cosines, and you're just going to be plugging numbers in here. The x over the magnitude of u, and so on and so forth. There's no other calculation. You don't have to worry about taking it any further with a calculator. All right, and I think I'll roll through the examples in the next video and finish this note up.